Now question number 11 বলছে for very sensitive and wide speed control the preferable control method is. Now the preferable control method is Ward-Leonard control. Ward-Leonard control. So in case of Ward-Leonard control, the shaft of generators and motors are mechanically coupled. This you need to remember. Ward-Leonard method. Shafts of generators and motors are mechanically coupled, and this is used for very sensitive and wide speed control. Question number 12. If the load current of transformer decreases, then the power factor will, option C, will remain unchanged, because load current has no relation with the power factor. Question number 13. The most suitable location for the power factor improvement device is. This is option A, near the electrical appliance which is responsible for low power factor, and also option B, at the receiving end in case of transmission lines. So the correct option is both A and B. Now question number 14. Which tariff is most ideal for the consumer? The tariff which is most ideal for the consumer is our 3-part tariff, not 2-part tariff. You should remember. Question number 15. It says a 125 kilometer long transmission line is loaded at 110 kV. If the loss of the line is 20 megawatt and the load is 175 MVA, the resistance of the line is. So in this question, it is not said about the whether this is a 3-phase or whether it is a 3-phase. So this is said that a 125 kilometer long transmission line. So they are saying about a single transmission line. So we need to find the current, because we know that power loss is I square R. So from there we can find the resistance. Now how to find the current? Now this MVA is the power. Okay. And this voltage is our line voltage. As this is not said a 3-phase, so this is not a line voltage. It is just V. So we need to find the current. So in order to find the current, what we will do, we will just divide the MVA, apparent power, by the voltage, because as it is said, as it is not said about any three-phase supply, so this voltage is not our line voltage. But if uh, it was said of three-phase supply or three-phase, if it was said of three-phase supply, then this MVA would have been divided by root 3 and the line voltage in order to find the line current. Okay, understood. But as here it is said about a single transmission line, so we are not taking this voltage as the line voltage. We are taking this as the phase voltage. And that too VI. So in order to find the current, we will just divide the MVA with the kV, and we will be getting something about 1.6 into 10 to the power 3 ampere. Now this is the current. So in order to find the resistance, we will divide this, the power 20 megawatt, by our current square. Then we can find the resistance, because I square R is equal to our power loss. This is the power loss. So we will get an answer 7.81 ohm. Then the correct option will be option B, 7.9 ohm per phase. Now question number 16. It says of the voltage and current in an AC circuit are given by V is equal to 200 sine omega t plus 30 and I is equal to 10 sine omega t minus 60, then the power factor of the circuit will be. So we need to first draw the phasor of this. So how to draw the phasor of this? Now this will be the sine omega t, and as it is said that V sine omega t plus 30, V is equal to 200 sine omega t plus 30. So V will be leading this one by 30 degree, and this one I is equal to 10 sine omega t minus 60. This will be lagging the sine omega t by 60 degree. So the angle between V and T will be total 90 degree. And now cos 90 degree is equal to 0. Therefore the power factor will be 0 power factor. So then the power factor of the circuit is option C, 0. Okay. Now this is an interesting question. We need to find the current through the resistance RL. So for this, we can apply any rule, Norton rule, Thevenin's rule. In case of Norton rule, what it says is that a Norton circuit should have a current source in parallel with Norton resistance and in parallel with the load resistance. And in case of Thevenin voltage, it says that the Thevenin voltage VTH should be in series with a Thevenin's resistance RTH and in series with the load resistance RL. Okay, now suppose we apply Thevenin's rule here. Then what we need to do is that we need to find VTH. For finding VTH, what we will do, we need to open circuit this resistance RL. Okay, we need to open circuit this resistance RL. So if we open circuit the resistance RL, the circuit will look something like this. Here the rest of the circuit I have not drawn because this part is not required, because we are getting the terminal voltage VT. We are getting the terminal voltage 1 volt here, and this resistance is in parallel with this one, and this one is also parallel with this one. So if we find the resistance across this resistor, we will find the VTH. That is the thing that is shown here. So if we want to find the resistance across 2 ohm, then what we will do, we will apply voltage divide rule. That is 1 into 2 by 2 plus 2. 1 into 2 plus by 2 plus 2. That is 1 by 2 volt, that is 0.5 volt. Now this is the Thevenin's voltage. But if we had applied Norton's rule, then what would have happened? According to Norton's rule, we need to short circuit the resistance RL and find the current IN. IN will be this one, which is flowing through the resistance RL, load resistance RL. So in order to find the IN, we would have applied mesh rule. For applying mesh rule, you know how to apply mesh rule, so I won't say. So in order to apply mesh rule, we will be assuming current in this mesh as I1, this mesh as I2, this mesh as I3, this mesh as I4, which is I4, where I4 is equal to our Norton's current, and we would have calculated the Norton's current as we have calculated VTH. So coming back to the Thevenin's theorem, we have calculated VTH. Now we need to calculate the RTH. Why we all are doing this? Because we know that in order to find the Thevenin's current ITH or the load current, the formula is VTH by RTH plus load resistance. This is the formula. So we have calculated the VTH. Now we need to calculate the RTH and then RL, load resistance, whose value is already given. So now to calculate the RTH. Now how to calculate the RTH? In order to calculate the RTH, what we need to do is that we need to find the equivalent resistance between these 2 points, which is already open circuited. These 2 points. Okay. So in order to find RTH, this thing should be remembered, and which is true for both the theorems, Norton's theorem as well as Thevenin's theorem, that the current sources will be open circuited, this one will be open circuited, and voltage source will be short circuited. So if this one is short circuited, then this portion of the circuit is not required, because current will always flow through this short circuit only. So we will find that this resistance is parallel to this resistance when we find the equivalent resistance between these 2 points. That is, this becomes like this. Here there was the voltage source which we have shorted, so this becomes like this, RTH. So we find the RTH as 1 ohm. 1 ohm. So now we will just put the value, and we will get the value of RTH as 1/3 ampere. If this one we would have done with Norton's theorem, then Norton's current, I have said how to find the Norton's current. We would have found the Norton source current here. Then we need to find the Norton resistance, which will be in parallel to this one, this current source. And finding Norton resistance is same as finding Thevenin's resistance, same to same, and we will get the value of the Norton's resistance, and this is the load resistance. So the circuit will be something, this portion will not be there, this one, this resistance, this resistance, this resistance, this resistance, something. This one will be the Norton's source, current source, this one will be the Norton's resistance, this one will be the load resistance. This value will be changed because we will put the Norton's resistance value here, and this one will be the load resistance. So the current that is flowing through this load resistance, we will find this one by current divide rule. The current, Norton's current, will be into the Norton's resistance. The Norton's current will be multiplied by the Norton's resistance by the total resistance, that is Norton resistance and the load resistance. We will get the value of the current here. Question number 18. So the correct option here, it was 1/3 ampere. D. Which type of insulators is used on 132 kV transmission lines? Generally, above 33 kV, we use disc type or string type. You should remember, disc or string type. These P-type insulators are used up to 33 kV, and shackle type of insulators are used in the distribution lines where the voltage is very low. Question number 90. So the correct option here, it will be disc type, which is used above 33 kV. 134. So the which type of insulators is used for on 132 kV transmission lines? It will be disc type, option B. Which of the following distribution system is more reliable? So the more reliable distribution system is our ring main system. Now question number 20. If two 300 volt full scale voltmeters V1 and V2 having sensitivity of 100 kilo ohm per volt and 150 kilo ohm per volt are connected to measure 500 volt as shown in figure 2, then Now the unit of sensitivity is ohm per volt. So here it is said that how much the value will be the measured value of V1 and V2. So the value of this V1 will be 100 divided by 100 plus 150, 250 into 500. Okay, which is here comes V1 will measure 100 by 250 because this one 100 kilo ohm per volt plus 150 kilo ohm per volt 250 by a into 500, that is 200 volt, and V2 will measure 150 its sensitivity by total sensitivity into 500 is equal to 300 volt.